Thank you. I guess you can see the screen and hear me, right?
Yeah.
I will talk about this recent work which we put on archive last month. It's called Fundamental Limitations on Entanglement Extraction from Purity. And so the outline of my talk is first I will introduce some basic notations. And of course, if you have any questions, please stop me in between. Yeah, I think that would be very nice. And then I'll talk about something called spectral certification of separability. So just by looking at the eigenvalues, you can certify separability of certain quantum states. So I will give I'll talk briefly about this. And then I will talk about this task called entanglement extraction from purity. Right? So this is an operational task. And then I will somehow relate both these things, the idea of spectral certification and the idea of entanglement extraction from purity. And finally, I will end with some final remarks. All right. So the setting is the following. We have a bipartite setting. So you have a bipartite system, Alice and Bob, right? And we all know that the state rho I b is called separable if it can be written in this form as convex combination of product states, right? Where sigma I is a state acting on the Hilbert space of Alice, and tau I is the state acting on the Hilbert space of Bob. If you can write your state like this, it's called separable. If you cannot write like this, then it's called entangled. So we also know the states which you cannot write like this, the so-called entangled states, are also quite useful. In fact, they are necessary for many tasks, such like quantum cryptography or metrology. You need entangled states to do such tasks. So it's a important resource to have. Now the question is, I give you a state, an arbitrary state of some dimensions dA and dB, and then I ask you, is the state separable? Well, to check separability is a hard problem. Yeah, there's no efficient way through which you can say a state is separable or not. But what we can do is we can give some weaker conditions. We can give some necessary conditions or some sufficient conditions to say when a state is separable or not. For example, a very well-known necessary condition on separability is called PPT. So if a state is separable, then what you do is you take the state, you do the so-called partial transpose, and then if you get a positive matrix, then it's for every separable state, the partial transpose has to be positive, right? So it's a necessary condition for separability, but it's not sufficient. For example, if the partial transpose of a state is positive, it doesn't mean it's separable. It's just a necessary condition, right? Similarly, we can also get some sufficient conditions on separability. A well-known separability sufficient condition is the following, which is called as a separable ball. What it essentially says is, if your state has sufficiently low purity, then it's always separable. So if you take the state and calculate the trace of rho square, and if this trace of rho square satisfies this inequality, then you know that the state is separable. You don't need to know any other information. If this happens, then you know it's separable. So this is a sufficient condition on separability. And note that this purity, this trace of rho square, only depends on the eigenvalues. It doesn't depend on the eigenvectors, right? So if your eigenvalues satisfy this inequality, regardless of what eigenvectors you choose for your state, it always is separable. So just by knowing the eigenvalues, and if it satisfies this inequality, you can certify a state is separable. So this is one example of a spectral sufficient condition on separability. Yeah. And one of the central results of our work is the following sufficient condition. It's a new sufficient condition which we introduced in our paper, which is the following. Take a state, any bipartite quantum state of any dimensions. Take the largest eigenvalue and the smallest eigenvalue, lambda max and lambda min, yeah? And take the ratio of them. If the ratio is upper bounded by this d plus 1 by d minus 1, where d is the smallest local dimension. Yeah, Alice and Bob have dimensions d and db. Take the smallest local dimension, that's a d. Now, if the ratio of the eigenvalues, if this satisfies this condition, it has to be separable. Regardless of what eigenvectors you choose, what the eigenvalues can be, doesn't matter. All right. This is again like this kind of purity ball where you just need to know the eigenvalues and you can compute a simple inequality, and then this certifies that your state is separable. Now let me do some simple remarks on what we have. Firstly, note that this first condition of purity ball, it depends on the global dimension, dA and dB. But our sufficient condition only depends on the smallest local dimension, right? Why is this important? So in fact, all the previously known sufficient conditions, if you can look at this recent paper by Anna Sanpera, this one, they have many more sufficient conditions in separability. They all depend on the global dimension, right? And as a global dimension becomes bigger and bigger, the condition becomes smaller and smaller. So this inequality, this thing somehow shrinks to zero, right? This is what happens with all the known sufficient conditions in separability. In contrast, our criterion only depends on the smaller local dimension. It doesn't depend on the larger dimension. So if you have a system with unequal dimensions, so Alice and Bob have different dimensions, then it can certify separable states which previous conditions cannot certify. To see this, let's consider this trace rho square condition. Take the trace of rho square up about this condition. Now fix dA and increase dB. This thing goes to zero, right? So when dB is very large, it doesn't certify anything except the maximally mixed state. But our condition doesn't shrink. Therefore, you can detect states with the large dB limit, which cannot be detected by the purity ball. This is where these conditions are somehow independent to each other, right? And a few applications. How does this help us? Let's say you have a multipartite state, right? N-partite state, right? And compute the lambda max over lambda min of the state rho. Take the lambda max and lambda min and compute the ratio. And let's say you have a natural number L which satisfies this inequality. Yeah, let's say you can find a natural number L which satisfies inequality. Now what it says is, if you make a bipartition, if you make a cut in this multipartite state, such that one side has a dimension at most L, then in that cut it has to be separable. This is what it will imply. It doesn't matter on the other side of the cut how many parties are there, because it only depends on the smaller bipartition. And it doesn't matter where the cut is. You can have any cut such that the smaller bipartition has dimension at most L. This implies that the state is separable across that cut. And if you further consider this multipartite state rho is a Gibbs state of a multipartite Hamiltonian H. Let's say there's a multipartite Hamiltonian H, and then you have a Gibbs state, let's say, and the Gibbs state is rho. Using this, you can actually find a lower bound on temperature. So if the temperature is above this quantity, then it has to be separable, this Gibbs state. And what is H infinity is the operator norm of H, right? And this L is the cut which you choose. So what it says is, let's say you have a multipartite Hamiltonian and there's a Gibbs state of it, and then you want to, then there's a cut in which you want to know if your Gibbs state is separable or not. Then if your temperature is beyond above this value, it certifies that your Gibbs state has to be separable across this cut. It just follows from this equation 2. Yeah. Any questions? Okay. So this is yeah.
So you if you go to the previous slide,
Yeah.
how do you prove that this condition that you are getting, lambda d minus 1 by d plus 1, d plus 1 by d minus 1, right?
Yeah.
Means of course you will be showing, right, this lambda max by lambda min. I am curious to know how you are getting this condition, lambda max by lambda min is less than or equal to d plus 1 by d minus 1.
You want to know how we proved it, right?
How yeah.
Yes. So it essentially follows from the one norm of witnesses. So what we show is, you take any entanglement witness, and we show that you take entanglement witness. Let's say you normalize it by trace to be 1, right? And now calculate the one norm.
Okay.
We show that the one norm of any entanglement witness cannot be more than the smallest local dimension. So one norm of W cannot be more than D, smallest local dimension.
Okay.
Once you show this property of one norm of the witness, it just follows from there. The crucial idea is to show that yes, the trace norm, yeah, the absolute value of eigenvalues, the summation of all the absolute value of eigenvalues. We show that you take any entanglement witness, take the trace norm, it cannot be more than the smallest local dimension. Once you show this, there's a very simple way. Once you have conditions on witnesses, we can get sufficient conditions on separability using this. So it follows from there. The proof, you can check the paper and there's a clear proof. I mean, it's not a difficult proof, but essentially follows from this fact.
Okay.
Yeah.
So I just wanted to know how that intuition came.
Which intuition? You mean the intuition of the
This
one norm or intuition?
the intuition of the entanglement weakness and the one norm thing.
Yes. So the thing is, if you show any necessary conditions on entanglement witnesses, so one norm upbounded by D is a necessary condition for entanglement witness, because any entanglement witness has to satisfy this. So necessary conditions on entanglement witnesses implies sufficient conditions for separability on states. So whenever you get a necessary condition on entanglement witness, you can imply a sufficient condition on separability of our states.
That part I understand. Yeah.
And the intuition essentially was we wanted a condition on the ratio of lambda max and lambda min. So this was the quantity we are interested. I will tell you why this is interesting. So this is something called monotone impurity theory. This lambda max by lambda min. So we wanted a condition of this function as an upper bound on this function. And then after some calculation, we realized actually one norm on witnesses will imply some sufficient conditions on this. So the intuition was in the beginning, it was not clear, but after certain, basically this lambda max by lambda min was something interesting for us, which we wanted to get some conditions on it.
And
then using this one norm of witnesses, we can come up with a sufficient condition like this.
Please.
Any more questions? Okay, then yeah, perfect. Yeah, this is essentially so one can as an application one can certify separability of multipartite states in certain bipartitions which you choose. Okay. Now the question is, we have this sufficient condition, but does it have any operational meaning? So is there any task in which this condition comes out naturally, right? Instead of this arbitrary, I mean, for now it looks like this arbitrary condition which one derived, which is sufficient condition. Okay, but is there any more deeper meaning for this condition? And this is what I will try to show, that in fact this condition has a clear operational meaning. And what is this is essentially the following question. So one asks this following question: how much purity you need to have in a system so that there is some entanglement? So if you have no purity, so let's say if you have a maximally mixed state, then you cannot have any entanglement, right? So it already says that there should be certain amount of purity in your system so that there should not, in order for it to have certain entanglement, some non-zero amount of entanglement. The question is how much purity you need to have in a system. This question is very closely related to this idea of absolutely separable states. So what are these absolutely separable states? So these are the states from which no entanglement can be generated via any purity non-generating process. This is the definition of absolute. So absolute separable states are those states, mathematically speaking. So if a state rho AB is absolutely separable, then it remains separable under any CPDP map which cannot generate purity. So lambda I equal to I essentially means when you give it a maximally mixed state, you get back a maximally mixed state. So it cannot generate any purity. Under any purity non-generating processes, this absolutely separable states remain separable. So if you have an absolute separable state and you want to get entanglement out of it, you can only get by generating certain purity.
So, but so also you can say this in the sense that any global unitary operators will not be without any
Exactly.
so absolutely without any global unitary operators.
Yes, one can equivalently say this. They're equivalent statements. One can stick to that definition. Also, one can stick to this more general definition. Yeah, these two definitions coincide. And I like this definition because it's much more, it's neater and it's much more general, right? Because global unitaries are a very specific form of this unital channels. But you can have unital channels which are beyond unitaries, and still absolute separable states will not generate any entanglement. So axiomatically speaking, if you can do processes which cannot generate purity, then you cannot generate entanglement out of these absolute separable states. It's sort of a very axiomatic definition of this absolute separable states. Right?
Right.
But the thing is, these absolutely separable states are not well characterized. There's no good characterization of the states. If I give you a state and ask you, is it absolutely separable? There's no good way to know it. It's a very hard problem, yeah. But similar to separability, one can again use this PPT condition to provide some necessary conditions for this absolutely separable states. What one can do is, instead of absolute separability, one can define something called absolute PPT. What they are essentially, a state is absolutely PPT if under all purity non-generating processes it remains PPT, right? You can just analogously define absolute PPT states. Unital essentially means purity non-generating process. It's short form for purity non-generating process. Now, if one of the local dimensions is 2, then we know that absolute separability and absolute PPT are the same. This was shown almost 10 years
So
ago by now.
2 cross B, this is same.
Yes,
AS and APP is same. But the
yes,
question is open in case of if there is one of the local dimensions not 2.
Yes, for higher higher dimensions, this is an open problem. Because absolute separability and absolute PPT
And
are
this
the
is
same.
one of the very famous open problems. Still.
Yes, yes, it's actually in one of this IQOQI Vienna list of open problems. Yeah. It's an open problem to solve. Yeah. So we don't know if absolute separability and absolute PPT are same for arbitrary general local dimensions. Okay. So one interesting observation is, take this 2-qubit state, right? It's a flat spectrum state of rank 3, right? And this is known to be absolutely separable. If you go to this paper for 2 cross 2 states, they completely characterize absolute separable states. And this is a known absolutely separable state. That means what? Under any unital channel which doesn't generate purity, you cannot entangle it, right? But now consider such a channel. So consider a completely positive map. So we construct this completely positive map in our paper where if you give it identity, it will give you something proportional to identity. But if you give you a state, if I input the state rho, it gives you some rho W, where rho W is an entangled Werner state. Just earlier, I told you that under processes which don't generate purity, you cannot entangle it. But now it seems like a contradiction, right? This process doesn't generate purity, but it generates entanglement out of this state because you get a entangled Werner state. So the question is, what is the catch here? The catch is a very simple observation that, well, this is a completely positive map, but it's not trace preserving. It's a trace non-increasing map. Therefore, it's a unital process associated to a quantum measurement. It's somehow it's a stochastic quantum map. So this quantum map can fail with some probability, but when it succeeds, you will get an entangled state.
Yes.
And still, it is unital. It doesn't generate purity, but it's not a deterministic quantum channel. Well, this is interesting now because what it essentially says.
All these results that we are having for the absolute, these are for non-stochastic processes, right?
Yes, it's only for deterministic unital channels. This is essentially the key observation of our paper, that absolute separability is only entanglement non-generating under processes which are deterministic. If you allow for a probability of failure, you can generate entanglement out of these states. So this says that absolute separability does not capture the ultimate purity-based limitations on entanglement generation, right? If you allow for certain probability of failure, you can still generate entanglement out of restricted purity.
Correct.
And such, yeah, any questions?
No.
And this idea of using probabilistic protocols to overcome restrictions was shown in previous works. So if you go to this paper by Bartosz Regula, this PRL, and he also has a PR, I think a quantum paper accompanying it, he actually shows that by using, instead of LOCC, if you allow for stochastic LOCC, then you can actually increase distillable entanglement and blah, blah, blah. So so these limitations on what you have for LOCC, you can get over them by allowing for stochastic processes. So this idea of using probabilistic protocols to overcome deterministic limitations have been studied in different cases earlier.
I think Chidambar also did that work, right?
I guess so. It's been in a huge focus in last 4 or 5 years, I guess. So there have been multiple works. I guess I would expect like this, something like this. Yeah. The first 2 papers were I think a few years ago were by Bartosz, and he has a quantum paper which is
he showed that the entanglement monotones can increase under SLO60.
Yes. A lot of entanglement measures. For example, disable entanglement can increase, right? So yeah, exactly. Yeah. So this is essentially the similar motivation to our project, that you can use probabilistic protocols, and you can overcome the restrictions in deterministic case. So this motivates us to define a more stronger set. We call it completely absolutely separable, right? And what is completely absolutely separable is the states which cannot generate entanglement with any non-zero probability under any probabilistic unital channel. So this is the most fundamental restriction you can have. Yeah, even under probability of failure, if your process is unital, you cannot generate entanglement.
So this is a subset of your AS.
Yes. So for example, this state which you have is not completely absolutely separable because there's a probabilistic channel which generates entanglement. Completely absolutely separable are essentially states which cannot generate entanglement even under probabilistic processes.
So, Barun, one
Yeah.
quick intuitive question. So,
Yeah.
so what is the relation of this completely absolutely separable? And if you try to define completely absolutely PPT?
I will come there. I will come there at the end. This is a good question. I will come there.
Yeah.
For now,
Okay.
we can just define it like this, right? In this operational
Mhm.
way, right? For now, we just need to say that, okay, well, a state is completely absolute separable if any process which doesn't generate purity cannot entangle it, even though if it's probabilistic, it doesn't matter, right? One can define a set like this. Mathematically speaking, this is what it means. A state is completely absolute separable if any process, any unital channel, unital essentially means if I put an identity, it has to give you something proportional to identity. Even if it is probabilistic, you need to, right? Even under probabilistic processes, it remains separable. You cannot entangle it. S is for separability. So this is the definition of it now. Now let's study this set. Well, it turns out, and so getting necessary and like completely characterizing this absolutely separable state is a hard problem. But turns out this completely absolute separable states have a very simple characterization. And this is the main theorem of our work. A bipartite state rho AB is completely absolutely separable if and only if our sufficient condition. So this set is completely characterized with this condition. If you take a state, you calculate lambda max by lambda min. If it is no more than d plus 1 by d minus 1, then it is completely absolutely separable. If it is more, then it is not. It's a complete characterization of the set. So the sufficient condition which I proposed before, it's not just one more sufficient condition, but has a clear operational meaning in terms of this task. And this is actually the main result.
So if I ask this question, so just like looks like this completely absolutely separable state is a subset of the absolutely separable state, right?
Yeah.
Is first question is this set is convex and compact?
Yes, it is convex and compact. Yes, because if you have two states which you cannot generate purity, or which you cannot generate entanglement, it just follows from this equation, this thing. You apply a channel, it acts linearly on it, right? And if both sides are separable, then the total thing is also separable. So it's convex. And if you look at this theorem, the lambda max by lambda min is upper bound, and this inequality is it's not strict. There's equality also, right? Therefore, it's also compact. Yeah, it's also convex and compact.
Okay, and so then in principle, you will be able to detect those states which are not completely absolutely separable state, but absolutely separable states.
Yes, you just check this. Just check this.
You can witness operator for them.
Yeah.
Those
You
which are
can
lying in the fringe in the ring means
yes, you can calculate witness.
There is a chance to detect those states with the help of witness operator, because these states probabilistically you can enhance the entanglement.
Yes, exactly. Yeah, you can generate entanglement. Yeah, states which are not completely absolutely separable, there always exists a channel which can do this. Yeah. And yeah, so graphically speaking, so you have this absolutely separable set within the blue line. This we don't have a good characterization, but complete absolute separable is essentially a subset. right? And this is given by our lambda max by lambda min condition. And this purity ball, which I defined in the earlier, is something like this. So there are states which are completely absolute. So this rho tilde is completely absolutely separable, but not in the purity ball. So it's detected by our sufficient condition, but not by the purity ball. And yeah, so this rank deficit state, which I defined before, is absolutely separable, but not completely absolutely separable. So it's way to somehow graphically show these things, yeah. And for example, if you take this state, this identity minus 5 plus partial transpose, this is actually on the boundary of all these three states. It's completely absolutely separable, it's on the purity ball, and it's also absolutely separable.
So can you tell me what is the purity ball once again? I missed
Purity
that
ball
part.
is essentially states which satisfy this condition. Trace rho square upper bounded by this.
Ah.
That's why I drew it like a ball.
Now, what about the convex and compactness of this particular set purity ball?
Yes, it's convex and compact because purity and the convex combination cannot increase. And it's compact because of equality. Yeah, all these sets are convex and compact. Yeah. Okay. Any more questions? Yeah.
Yeah, hi. I have a question.
Yeah.
The condition you have showed, I mean, the CAS condition, that also, I mean, similar to what you found at a sufficient condition of separability, right?
Yes, it is the same condition. Yes.
In the scheme of the proof, you have adopted the technique of, I mean, you have taken the entanglement witness and it's one norm, and I mean, with that you have found this criteria. Now, I would like to ask that, I mean, if you put some emphasis on some special characteristic of entangled witness, like, I mean, if it is decomposable or indecomposable, and this kind of special class of entangled witness, if you consider, will it give any advantage here, or I mean,
this one norm condition, it holds for all entanglement witnesses.
True, I understand. But the thing is that my question, if you further put any, I mean, any condition over the entanglement witness, will it give us something new, or I mean, it is just...
I can tell a bit about this. So, for example, instead of all entanglement witnesses, if you just look at PPT witnesses, right? Then essentially you're asking about when does it become NPT, right? So in fact, the one norm of PPT witness is also upper bounded by D. It's also strict because if you take 5 plus partial transpose, 5 plus is the maximal entangled state in the given dimension, and then you take the partial transpose, it actually achieves this one norm condition, saturates this. So even for PPT witnesses, this one norm condition is as it is. And then everything goes through, and they will have a bipartite state is completely, absolutely PPT, if and only if this condition is true.
Okay.
And you can play the game with any subclass. You can even define some other subclass of witnesses, and you can define completely, you know, all these things, and things, most of them will go through.
Okay.
Yeah.
Thank you.
So by the figure, are you suggesting that one of the extreme points of this completely absolute separable states are actually the absolutely separable states? I mean, obviously they have, but
yes, all completely absolute separable are absolute separable.
No. I mean, one of the extreme point of the CAS set is also the I mean, the extreme point of a AS.
Yes. This, for example, the state which I wrote down here is an extreme point of both these sets. They match at some extreme points, and this is one of them. So this state is absolutely separable and also completely absolutely separable.
But in these kind of sets, it is difficult to characterize the extreme points. In case of separable states, we have this kind of H states, which trace W low comes out to be 0, right? So what we call as the line of the separable ball, those are called H states, because if you take the trace with W, any entanglement witness, trace of W low comes out to be 0. So
if a witness is optimal, yes. Okay.
So characterizing this, how difficult is this characterizing these extreme points?
I mean,
So
we
we
haven't
can-
looked at for now, but for example, I think I don't think it would be very difficult because it's just this condition, right?
Mhm.
Any states which saturates this condition is an extreme point. You just calculate the lambda max and lambda min and take the ratio of it. If it saturates this condition, it has to be an extreme point.
Right.
So for this set, I think it's not so difficult because it just depends on the two largest two extremal eigenvalues. Take the ratio, and you can check if it's an equality. It has to be an extremal point. And one can see this. You take the state and you calculate the lambda max by lambda min. It gives you essentially d plus 1 by d minus 1.
You mean the pure state? The pure state. That
But this is not a
satisfies
pure
that.
state, right?
This is not a pure state, exactly.
No, this is not a pure state. This is for equal dimensions. It's so-called the Werner state on the boundary.
So Varun,
yeah.
Okay. So another question in this context, as I have asked you before, is the same kind of situation will exist for Agven?
For what?
For Agven, absolutely conditional von Neumann to be non-negative plus.
Oh, you can also define probabilistically like this.
Hmm.
One can do the same thing. Yeah, even probabilistically, you cannot generate conditional entropy or something like this. And because this conditional entropy, absolute conditional entropy states are completely characterized. There's simple characterization for it, right? Yes, and I would expect the same to have a very simple characterization for even this probabilistic when you go to the probabilistic case and put a more stronger constraint. Yes, one can definitely do this. Yes. So essentially, you ask under any probabilistic channel, you cannot generate negative conditional entropy. And then you can, I think there should be a simple way. Yeah. I mean, look, going to this probabilistic channels sounds like a difficult thing, but in fact, it makes a lot of things very simple. That's essentially the part that you can solve these sets very easily. Yeah. Any more questions?
Yeah, the previous question that how the relation of CAS with that if you define completely absolutely PPT.
Yes, that's where I'm going now.
Okay.
Yeah. So the first observation is the absolutely separable states, not the completely one, the normal absolutely separable states, they're not closed under tensor products. What does that mean is you can have absolutely separable states rho AB. When you attach a maximally mixed ancilla on just locally, the final state is not absolutely separable. Right? Because this is absolutely separable, this is absolutely separable, but then you expect tensor product should be, but not. If you put a tensor product of maximally mixed state, there are states for which this doesn't happen. So it's not closed under tensor products. Well, then you can ask, well, I enforce the closure artificially. So I ask, what are the set of states for which rho AB tensor IV remains absolutely separable for all DB, regardless of what dimensional maximally mixed state you attach locally, this has to be absolutely separable. What are such states? It turns out, take a state rho AB and attach a maximally mixed ancilla. This is absolutely separable for all DB is equivalent to saying this is absolutely PPT for all DB. And this is again equivalent to our sufficient condition. So somehow the sufficient condition ends up in very different ways. If you enforce closure artificially and you ask, well, when can rho AB be absolutely separable under attaching all maximal mixed ancillas or all dimensional maximal mixed ancillas? This is equivalent to saying lambda max by lambda min is upper bounded by this. If this holds, then you can do this. If not, you cannot. There will be a maximal mixed ancilla you can attach, and it becomes not absolutely separable. And the same thing, and this is equivalent to PPT as well. So you take a state rho AB and attach identity locally, and then ask it has to be PPT for all natural numbers DB. It's equivalent to saying that lambda max by lambda min upper bounded by d plus 1 by d minus 1. And that's why we call this set which satisfies this sufficient condition as completely absolute separable in the same way as positive maps and completely positive maps. So this is absolute separability. It has to remain absolute separable under all identities. So it's completely absolutely separable. And that motivates us the name. And then from here, from this definition, you can see complete absolute separability and complete absolute PPT are the same, which is equivalent to the condition we had.
Any dimension.
For all dimensions, it has to be absolute
That is
separable, and
very
similarly for all
interesting because
dimensions.
if you do AS and APPT, we don't know the results.
Yes. AS and APPT is an open problem, but CAS and CAPPT are the same.
Same. Why do you think so? Why it is happening? Intuitively, what does
Well,
it tell you?
Typically, what happens is when you attach maximally mixed ancillas, the eigenvalues repeat, right? So the largest eigenvalue, let's say, is lambda1 of the state row. If you attach identity to it, then the largest eigenvalue repeats dB times, right? And similarly, the smallest eigenvalue also repeats dB times. And because the eigenvalues repeat, all these calculations become simple, and somehow the calculation only depend on the first and last eigenvalues. Because they repeat so many times. And this makes the calculations very simple, and one can show that these two things become equivalent. Because the largest and smallest eigenvalues repeat, you can make them repeat as many times as you want by increasing the dB.
But why the natural numbers? That should happen for the for element.
No, but dimension can only be a natural number, right?
Yeah.
I mean, dimensions cannot be 0, or it can only be, I don't know, 2 or 3 or 4. So it has to happen for all attaching any maximally mixed state, regardless of what dimension you have. Any questions?
Question again. That is, do you have any comment regarding absolutely non-Schmidt rank increasing states in this slide?
Oh, Gus, go ahead. Absolutely Schmidt rank K states, you mean?
Yes, I mean, for which under applying global unitary, Schmidt rank will not change.
Yes. So this is what we are working on currently. So what we are trying to do is we are trying to extend sufficient conditions which we have for separability. Not only this, but we have various other sufficient conditions, right?
Yes.
And we want to extend the sufficient conditions for Schmidt rank K states.
Okay.
So sufficient conditions for Schmidt rank K. And once you have this, you can make you can then define absolute Schmidt number K, right? Because the eigenvalues don't depend on the unitaries. So I mean, I don't have any clear comments now, but this is what we're working to. So once you extend sufficient conditions of separability to sufficient conditions of Schmidt number K, and if the sufficient conditions only depend on eigenvalues, then under any global unitary, the eigenvalues don't change, right?
Right.
So the sufficient conditions will give information about absolutely Schmidt number K.
Yes. Okay.
So this is what we're currently working on. Yeah.
Thank you.
Any more questions? All right. So essentially we show this, yeah, and yeah, this is where I end my talk. And just to conclude what I have, so we have a new sufficient condition on separability, and this condition is good because we can detect states which cannot be detected earlier. You can certify separability of certain states, but just by looking at the spectrum. And then we show that actually some probabilistic protocols can produce entanglement out of some absolutely separable states. Therefore, we define this notion of complete absolute separability, and then we show that actually this can be completely characterized, fully characterized. And then we can actually show a connection between this notion of absolute separability and complete absolute separability by closing under tensor products. And then at the end, we show that this complete absolute separability and complete absolute PPT are the same, which is sort of showing a weaker, I mean, the original conjecture is absolute separability is equal to absolute PPT, but we show sort of a weaker form of this conjecture by showing complete absolute separability and this complete absolute PPT are the same. So with this, I end my talk, and this is the archive link.